Hi class. My sound was not going through my phone and it gives a funny echo. So if you hear that, let me know. We're going to talk about significant figures in my video so you can see it. And again, significant figures aren't going to go away. For the entire time you're in chemistry, they really push it for healthcare so that you're being very precise and careful when you're recording digits. You're going to be using significant figures. So pennies come in whole numbers. Many things come in whole numbers. And when they come in whole numbers, it's a counting object and it doesn't have significant figures. But if it's something you can weigh, for example, if you're going to sell your gold, you're going to want them to have a lot of precision when they weigh it, then you want significant figures. You want a balance with a lot of digits so that you can make sure that you're getting your money's worth. It's the same in science. We want to make sure that we're being very careful with what we're weighing. Same in healthcare. We want to make sure the medications are being very carefully distributed. So scientific numbers are reported so that every digit is certain. That means if you take something off of a digital balance in the laboratory, you need to write down every digit. So anything that's digital, we never round. But even when it's digital, the last digit is always estimated. So that digital device is estimating that last digit. If it's not digital, and we're reading tick marks, and we'll talk about that, you're estimating the last digit. But we just know that whatever the final digit that is written, the smallest digit, that's your estimated digit. Again, you have more precision if you have more digits. So this is a concept that can be a little tricky for students if they haven't done it before because they use old school balances. And they really do use old school balances in many things. For example, in healthcare, they might still use the slider when they're weighing a patient, but they also probably use it in the lab when they're weighing out medications. So what you need to know are a few things. One is, if you're looking at this balance right here, you've got tick marks. These little lines are called tick marks. And you also want to know that you can read in between the tick marks, but you can't read any smaller than that. So the first thing you want to do whenever you have a balance with a tick mark, we have some in the laboratory too, you're going to keep encountering these in science, is you want to find out what the tick marks are actually reading. For example, are they reading 1 gram? Are they reading 10 grams? Are they reading 0.1 grams? So you count. You go 0 to 10. Okay, so the little tick marks in between are doing 1, 2, 3, 4, 5, all the way to 10. So they're reading 1 gram. And every device will have a different tick mark, meaning some will read for 1 gram the one place, others will read to different places. So that's the first thing you always want to check, is what is that tick mark representing. Here it's 1 gram, because we counted. If it reads to the ones place, so the ones place, then you can write down, and should write down, to the tenths place, which is shown right here, 1 place smaller. So we should always write down 1 place smaller when we're using a device like this that has tick marks. And if you know, it's not right on 1 gram, it's a little bit past. So the person who made these slides read it as 1.2. Someone else might see it as 1.1 or 1.3, and that's why this last digit is always estimated. Now we're going to go to another device. If you can really look closely here, you can see it's doing 1, 2, 3, 4. So it's reading even smaller than that because it's broken down in between with little tick marks. It's doing 1.1, 1.2, 1.3. So again, you would need to manually count on your device, and then you could declare, okay, it's reading to the 0.1 place, and that means you can estimate 1 place smaller. Smaller than the tenths place is the hundredths place. So the correct reading, they say, is 1.26. But it could be, it depends on who's reading it. Someone else could see 1.25. But even if it were right on 1.2, do you see the 1 here and you count to the 2 and it's in between the 0.2 and the 3. Even if it were right on the 0.2, you'd still need to say 0.20 to let the person know that you were careful and precise in your measurements. Now we're going to talk about the rules for significant figures. So all non-zero digits are significant. So any number like 582, there's no zeros in that, they all count. You would have 3 significant figures in 582. Interior zeros are significant. So in 101, 101, you would still have 3 sig figs because that 0 is in the middle. Trailing zeros, zeros to the right of a non-zero number that fall after a decimal place are significant. So if you wrote 1.00, you would still have 3 sig figs because if they bothered writing a decimal place and zeros after it, they measured it. Trailing zeros that fall before a decimal place are significant, so they're considered still zeros in the middle. So for example, if you had 10.0, it would still be 3 sig figs. Leading zeros, so zeros like if they said 0100, those don't count. And trailing zeros at the end where there's no decimal place, such as 101,000, we only know the 101 and 101,000 counts for the sig fig, so there's 3 still. But those zeros after, we don't know if they were measured. So we just say 3 or ambiguous, which means they might count, they might not count. They didn't indicate, so we only assume the ones that are indicated. We're going to try some. So exact numbers again, if you have a counting object, like a dozen roses, they say integral numbers. That means they're part of an equation. And what they should say is their conversion units. Defined, meaning their ratio. So if you have a ratio like 3/4 of a mile, someone runs 3/4 of a mile, that's exact. And then they say some conversion factors are defined. That means if the conversion factor was measured. Most conversion factors are not significant. And here's a little example of the rules. Here you have leading zeros. They don't count. So the only ones that count are these 2 sig figs. Here you have a 0 in the middle. It counts. And a 0 after a real number and a decimal. It counts. So the total is 4 sig figs. Here it should say 2.97. I don't know what the 7 is doing way over here. 2.97 times 10 to the 5th. 2.97 times 10 to the 5th has 3 sig figs if it didn't have this weird typo in it. 1 dozen equals 12 is unlimited or infinite sig figs because it's exact. 100.00. Now if they bothered to write the decimal and zeros after it, they measured it. So there are 5 sig figs here. All of them count. And here's ambiguous. We only know 1 for sure because it's a real number. But there's no decimal place. So we don't know about those 5 zeros. They may count, they may not count. If they don't give us any indication, we say there's only 1 sig fig.